In a previous video, we introduced the notion of a compact set, and here we want to look at a kind of standard result involving compact sets. Let's recall this definition first, though. So we say a subset K of real numbers is compact if every sequence in K has a convergent subsequence that converges to an element of K. So we won't actually use this precise definition for our proof. We will use this equivalent formulation that we also proved in a previous video. And that says that K, a subset of R, is compact if and only if it is closed and bounded. Okay, good. So let's see what our goal is. We want to suppose that we have K, a subset of real numbers that is non-empty and it is compact, and show that the supremum of K and the infimum of K are elements of K. So baked into this conclusion is that the supremum and the infimum actually exist. So we'll show that they exist and they are elements of the set K, which gives this notion of compactness some sort of nice behavior in that compact sets attain both their least upper bound and their greatest lower bound. And we are actually only going to prove that the supremum of K is an element of K because it's almost exactly the same to show that the infimum of K is an element of K. Okay, so let's go ahead and get started. So we know since K is compact, it is bounded. Well, obviously it's closed and bounded, but initially we're just going to use the fact that it's bounded. Near the end, we'll use the fact that it's closed. And so what that tells us is that there exists some real number m, which we could think of as quite large, such that the set K is completely contained in the open interval minus m to n. So we've put a huge circle around K, and that fits all of K. It's just that circle is like one-dimensional given that we are on the real number line. Okay, great. And so now notice that here, this tells us that the absolute value of A is less than M, and this is true for all A in K. In other words, M is an upper bound of K. But recall from the axiom of completeness, we know that every set with an upper bound has a least upper bound. So this brings into existence the least upper bound of K. So there exists U, which is equal to the least upper bound, in other words, the supremum of K. And I should say that this U is some real number. So again, that's by the axiom of completeness. If there's an upper bound, there must be a least upper bound. And so all that's left to show is that U is actually an element from K. So we've just shown that the supremum exists. Now we need to show that it's in the set. And we'll do that by constructing a sequence that converges to this supremum. But now we can say for all natural numbers little n, we have x sub n in K, that compact set, such that the following is true. X sub n is less than or equal to U. Well, so that inequality is always going to hold because U is a upper bound for K. In fact, it's the least upper bound. But then this x sub n is bigger than or equal to U minus 1 over n. Let's talk our way through that. So we can bound this on the left-hand side by this U minus 1 over n because U is a least upper bound. And if it were impossible to put this bound on the left, then that would contradict the fact that U was a least upper bound. So let's maybe write that down. That's because U equals the least upper bound of K. Great. But now it's pretty easy to check that if we take the limit of this sequence xn, as n goes to infinity, we get U. So notice here, xn is between U minus 1 over n and U, but this part is tending towards U as n tends towards infinity. So you can check that more carefully if you want to, but I don't think it's super necessary at this point in the course. Okay, great. So now, what do we have? We have a sequence of numbers inside of K is converging to U, but what that means is that U is a limit point of K. So the definition of a limit point didn't have anything to do with the sequence, but an equivalent formulation that we proved had some sort of sequential notion to it. So we've got U as a limit point of K, but then since K is closed, it contains all of its limit points. So that means U is in K, and this is since K is closed. The definition of being closed is containing all of your limit points. So let's see what we've got. We've got U is equal to the supremum of K, and U is in K. So in other words, K, this compact set, contains its supremum. And a completely analogous proof will show that it also contains its infimum, or its greatest lower bound. And that's a good place to stop.